This is the Chem 1 lesson over states of matter. We're going to cover what temperature is in those units, what pressure is in those units, phase diagrams, including phase changes and different states of matter, and then last, phase diagrams. So first, temperature. Temperature has to do with the speed of particles. Temperature is defined as the average kinetic energy of the particles in a substance. So the faster they're moving, the higher the temperature is going to read. So you guys are going to have to be able to convert between Kelvin and Celsius. So to do that, you've got an equation. Whatever temperature in Kelvin is really equal to Celsius plus 273. So if we're going to take negative 37 degrees Celsius and convert that to Kelvin, so Kelvin is going to equal negative 37 degrees Celsius plus 273. You add those together. You're going to get 310 Kelvin. Now to do the opposite, since we have 298 Kelvin, that's going to equal our degrees Celsius plus 273, which really means we have to subtract 273 from 298, and you're going to get 25 degrees Celsius. So I always just remember that Kelvin is 273 larger than Celsius. Next, pressure. Pressure is just defined as the force exerted by the collision of particles. So picture you've got gas particles in a balloon. They're going to be bouncing around. The more particles that hit the sides of the container, the higher that pressure is going to be. When converting between units of pressure, you will be given the conversion factors you need. 1 atmosphere, that's 1 unit of pressure, is equal to 760 millimeters of mercury. So mm is millimeters. Hg is mercury. That has to do with how many millimeters high atmosphere can push mercury up into a vacuum tube. And the last one is 101.3 kilopascals. Now all three of these things are equal to each other, so you can use any 2 out of the 3 you need. You don't need to memorize this. That'll be given to you on test if you need it. So converting for pressure, you do have to use dimensional analysis. So we could start off with 1.5 atmospheres. Converting it to kPa, we got to cancel out our ATM. In this case, kPa is going to go up top. Pulling those conversions, 1 atmosphere is equal to 101.3 kPas. So you've got to do that math. 1.5 times 101.3, you're going to get 151.95 kPa. Rounding the guy to 2 sig figs, you're going to get 150 kPas. Our second conversion is with millimeters of mercury. So we're going to start off with 780 mmHg. So we're going to have to put mmHg on the bottom down there and convert that to atmospheres. So ATM up top. We've got 1 atmosphere for 760 millimeters of mercury. So we take 780 divided up by 760, you're going to get 1.02631. Got to run that to 2 sig figs, so we're going to end up with 1.0 ATMs. So next, you guys need to be aware about phases, so solid, liquid, and gas, and then also those phase changes. So there's a lot of information on this diagram here. So we have solid, liquid, and gas. So solid, remember those particles are very close together. There's very little motion between them. Remember solids keep their own shape and their own volume. They're both defined. So a solid's not going to take the shape of the container, nor is it going to expand to fill the container. Now liquids, those particles, there's a little bit more motion with them. There's a little bit more space in between them. So liquids will take the shape of their container. So the water in the bottom of your water bottle will take the shape of the water bottle, although it will not expand to fill it. Gases, the third state of matter, those particles have the most motion in between them. They're the furthest apart. Gases both take the shape and the volume of the container they're in. So phase changes, you can have any changes going on between any of these guys. So first, going from a solid to a liquid, that's called melting. The opposite of that, liquid to solid, is called freezing. Now you guys have probably heard those terms before. Liquid to gas, that's called vaporization. Sometimes that's called boiling, same thing. If that happens, the change from liquid to a gas, when it happens without the addition of heat, that's called evaporation. And then last, gas to liquid is called condensation. So think about the dew on the grass in the mornings. Now, the two new ones you may or may not have heard before. Solid to gas, that's called sublimation. And the way I remember that is that's what dry ice does. Dry ice is very cold carbon dioxide. At normal atmospheric conditions, it goes straight from a solid to a gas. And then the opposite of that is deposition. So that's going from a gas to a solid. So those are probably those two new phase changes you probably want to review. Then you are given a phase diagram. So a phase diagram shows the relationship between temperature and pressure. So you look at your axis, temperature and pressure. You can see that the coldest temperatures, right, with the lowest pressures, generally speaking, you have solids, right? So solids are going to be those particles that aren't moving very much. And then the opposite, right, the hottest temperatures and the highest pressures, so way up here or way down here, you have gas. Sometimes that's called vapor. Then in the middle, you have a liquid. So you have defined solid, liquid, and gas. This is specific for every substance, so different chemicals will have different phase diagrams. And the lines here represent those phase changes. So if you're talking about going from a solid to a liquid, that's called melting. Going the opposite, freezing, is going from a liquid to a solid. So those two phase changes occur along that line. It just depends on whether you are heating up or cooling off that substance. So then the phase changes of vaporizing and condensation, those are the phase changes between liquid and gas. They're going to occur between that line. So vaporization or boiling would be going towards the gas. Condensation would be going towards the liquid. Sublimation and deposition are between gas and solid. So solid to a gas, that's your dry ice, right? Or the opposite, gas to solid is going to be called deposition. So you can see those phase changes on there. So here's a pretty one of that. So same thing, as pressure and temperature change, so we've got our pressure, we've got our temperature, we can see all the different pressure and temperatures, what state of matter, whatever substance would be, with our phase changes. This diagram has critical point, so that's the point where liquid and gas can no longer be separated. It's turned into a supercritical fluid, and that's because you have this fast motion like a gas, but the particles are close together like a liquid, so you can have that line does end. You have the triple point, so triple point is where you have all solid, liquid, and gas all at the same time. Also is on here. So you can determine the what kind of substance you have. You can also determine the density of that substance based on the slope of that line between solid and liquid. So they're highlighted here. If the slope of that line slopes in a positive way, so towards the liquid, that tells me that maybe if you start at the triple point and you add pressure, so we're going to go up here, as we go up, we're going to end up in solid. That tells me that the solid is the more dense state of matter. So in substance A, the solid is more dense than the liquid. Now, if you look at substance B, that line slopes the opposite way. So that means if we were to add pressure, right, so go up on this graph, we're going to end up in liquid as the more dense state. So substance B, you could say that the solid is less dense than the liquid. And there's very few substances that are true where the solid is less dense. I forget, it's bromine, and the big one here is water. So water is one of the few substances where the solid is less dense. So if you've ever frozen ice cubes, you know that the water tends to expand a little bit. And that's why ice cubes float. That's very unusual. Most substance, the solid version of it, is going to sink. It's not weird to us because we see ice water all the time, but that's actually a pretty unique thing about water. So that tells me, based on that slope of this line, that this is water. The last term is normal. So normal atmospheric conditions is 1 atmosphere. And the unit atmosphere comes with how much pressure is pushing on you due to the atmosphere. That's why it's called ATM. So 1 atmosphere is normal. So normal, if I ask a question about normal, that should tell you, okay, we're at this line right here. So you could tell me the normal boiling point. Well, normal boiling would be along this line too. Normal would then be right here. So you could say the normal melting point is 0. The normal boiling point, that would be over here, obviously between liquid and vapor, that's going to be 0 degrees Celsius. So based on if I can tell you a pressure, you can tell me the exact temperature that something is going to either melt or freeze at. In this case, it's 0. Boil at, in this case, it's 100. So this is water, guys. I can tell by the slope of the line, right, between solid and liquid, but also the fact that I know that water freezes at 0 and boils at 100 degrees.